Bismillahirrahmanirrahim. Assalamu alaikum. So first let's just quickly get it out of the way why I've been absent this last week. So here in our region it has been raining quite heavily this past few weeks, almost constantly, and because of that there's been a lot of load shedding as well as network connectivity issues. So yeah, because of those things I wasn't able to stream, and hopefully the conditions will be better in the coming week, and we will continue streaming uh, in a very consistent manner, let's hope. So yeah, last week we finished this functions in depth chapter of the Clojure workshop, and today I am planning to finish this chapter, mapping and filtering. And I'm little conflicted about should I keep on doing this or should I start Clojure from the ground up and continue that from where we left off, because other team members in the team Prometheus, a ClojureFam of which I'm a part, they're doing this, and I guess if we want to, they're following a strict, there's a strict, not strict per se, but a syllabus for ClojureFam, and they're doing that. And to measure our progress with them, I'll have to complete this one, as most of them aren't doing these exercises. So, but I think there's a lot more to learn in this workshop than here. So here macros are introduced in chapter 11. Here they're introduced in chapter 6, and I guess there are some, yeah, they're probably doing mapping and filtering in this chapter sequences, chapter 4, and we'll learn about mapping and filtering in chapter 4 as well. Yeah, just let's just start this and get it over with. Okay. Okay, in this chapter we'll learn about mapping and filtering and how to shape the data in Clojure so that we can perform some calculation or do something with that data. In traditional programming languages like C++ or Python, there's usually all of this is done in a for loop where we, for example, get the data and then shape the data and then do something with the data in a for loop. For example, incrementing I or controlling how the data will be processed using some control variable like I, which is, for example, usually the case we use I, but in Clojure we separate that into different functions. For example, here there's a, for example, one function would get the data and another function would shape the data, and most of the work would be done in shaping the data so that we can later on do something with that data. Okay, so that's the gist of this article. Map and filter. So map and filter are two of the new functions that we learn about today, among many other, I think. Map and filter, they take in a sequence and they return another sequence with some filtering or modification, let's say. Here, and the filter, we're using filter to filter out some of the values and only um, collect or get or return the values that uh, that follow some, what do you say, yeah, that follow some rules defined for the filter, and then we use map to transform those values so they can be used one after another. Okay, so can we run that without the brackets? I don't think we can. Oh yeah, we can run that, but it won't evaluate it. It would just return, treat all of this as separate expressions. For example, this is the first expression, which is a symbol to a Clojure function, clojure.core map, and this is the second symbol, and this is a vector. So to execute this, we'll have to use this 1, 2, and 3, and yep, it's incrementing here map first, and map takes as argument as the first argument of function and then a sequence, and here it's applying that function on each and every element. For example, it's applying increment on 1, 2, and 3. Incrementing 1 by 1 would result in 2, similarly 3 and 4 for 2 and 3. Okay, so if we don't provide another argument, third argument or second argument for map, which is a sequence, it would create something called transducer. We don't know much about transducers for now, and probably we'll learn about those later on. But the thing to note is that it won't give an error. This is Clojure.core map and then some function. Okay, let's call map on a function. Provided a function which simply multiplies the argument by 10, and let's provide a sequence as well. So yeah, it would map each of this element to this function and return the result of that function as a new sequence. So 1 multiplied by 10 would be 10, and 20, and 30, and 40, and 50, so on. And this is one-to-one equivalent. So if a map would always return, or the return value or the return sequence will have the same length as that of the input sequence. Okay, and we can, for example, count the length of some strings. Let's measure word length now. So this is a sequence of some strings, and we're mapping all of these elements to the function count. So what we're saying is count the number of characters in all of these strings and return a new string. So the size of the string or the size of the sequence would be the same as the input sequence. For example, here the size of the input sequence is 1 2 3 4 5, or length, let's say, and here 1 2 3 4 and 5, where this 5 is representing the length of this string, and then 7 is the length of this string, and so on. And here we are defining an anonymous function which simply appends the word and its length together. So the output would be, for example, here it would append let's, it would return a new string with let's and a semicolon, a space, and its count, or the size of that string. And now we'll look at filter. And filter, as expected, might contain or might return a sequence with fewer items or with a smaller length. So to call filter, first we have to call the filter, and then the first argument will be some keyword which we'll learn about. For example, here we're saying if this is I guess this is a function keyword. Let me quickly test it out. Keyword question mark, meaning this would return boolean, and we want to see if count is a keyword or not. Yep, keyword is a function. So here we're, for example, filtering if something is a function, if something is a keyword, and if it is, then it would only return that. For example, here this is not a keyword, so in the returned sequence we're not including this a. This is a keyword, this is not a keyword, this is a keyword, so we would only return B and D and F. And here if a truthy value, for example, is returned, and truthy values are all those values except false and nil. So everything except false and nil is considered to be a truthy value, even 0. So the difference between map and filter is that map changes the elements in a sequence. For example, here if we see that it's changing or working on this, for example, elements in the sequence already, but filter, it just includes or doesn't include some element, it doesn't change them. Okay, this is a new function odd, which would either return true or false based on if the argument to it is odd or not. Odd 5 4 3. Okay, so it expects only a single argument. Yep. And if we try to filter a sequence using this predicate function, we would only get the odd numbers in the list, 1 3 and 5. And there's another function called remove, which would remove only the elements that are odd. For example, where this function would return true, it would remove those elements, so we would only get 2 and 4. It would remove 1 3 and 5. Constantly true. Clojure's constantly flowing function returns a function that does nothing but return a single value, regardless of the number of arguments. So this is the value that we want to return. So constantly would create a function that would always return true. Doc constantly returns a function that takes any number of arguments and returns x, where x is the input to constantly, and here x is true. Okay, so here if we want to always return the whole string and we don't want to remove anything or filter out anything, then we can use filter and constantly true, which would return the whole sequence as it is, and constantly false would remove all the elements. Okay, so now we'll learn about some new keywords like TakeWhile and DropWhile. The TakeWhile and DropWhile functions, these are functions, not some basic forms like while or if, etc. I guess. Was there some while in do? Yeah, there was do, not while. There's no concept of looping. Yep. Anyways, so the TakeWhile and DropWhile functions follow the same logic as filter and remove, at least as far as their use of predicate goes. The difference is that they only operate at the beginning of a sequence, much like take and drop. The take function returns the first n items of a list, while drop returns the original list minus the first n items. So for example, if we call take 3 on this sequence, it would only take the first 3 elements, 1, 2, 3, and drop 3, it would drop the first 3 elements and return everything else. So TakeWhile starts at the beginning of the list and returns all the items as long as they satisfy the predicate. For example, here TakeWhile, an anonymous function, which checks to see if something is greater than 10, or if 10 is greater than something. Yep. So 294 12 3 99 and 1. TakeWhile starts at the beginning of the list and returns all the items as long as they satisfy the predicate. So 2 does satisfy because 10 is greater than 2, 9, 4, as long as they satisfy. Okay, so once a value is returned false, for example here 12 is not satisfying this condition, it won't execute the rest, I think. Yep. So because otherwise it would be same as filtering. For example, if it was returning, let's say filter and the anonymous function where we're checking to see if 10 is greater than some argument, and 2 9 my bad 2 9 4 12 3, 99, 1. So it's returning 2, 9, 4, and this 3 and 1 as well, as expected. So if TakeWhile was behaving like that, for example, always checking every element, then it would be the same as filter. But I guess what it's doing is it would check to see, or it would take the elements while some condition is true. Okay, so it would take this and return that, take this and return that, take this and return that, because here the condition is being true, or the predicate has a truthy value. But when it becomes false, it would stop executing because it's not returning 3 and 1. And drop while removes the same items from the beginning. Okay, drop while would remove these elements while this condition is true. So it would drop this, it would drop that, it would drop 4 as well, and here when the condition would be false, it would stop dropping and return everything else. Let's just quickly define this symbol or variable called students, which contains a list. For example, here it's a list of dictionaries or maps. Maps. And let's not use the word lists, but be explicit and use the word vector. So it's a vector of maps where each map contains two keys called name and year and their corresponding values. Write a predicate that translates the idea before 2000. Okay, so we're writing an anonymous function which checks to see this is getting the year value. Here, for example, if I pass student to it, which is a vector, it would pass this thing, first element, to this. For example, TakeWhile or filter or map or whatever, it would pass this element to this predicate function, and here we're getting this year keyword or the value associated with this year keyword and checking if it is less than 2000. And then we can use, for example, TakeWhile function using that predicate, getting the year from the provided input or element and checking to see if it's less than 2000, and then we'll pass in the sequence to the TakeWhile function, and it would only return the students or elements whose year value is less than 2000. So here the first one is less than 2000, second one is less than 2000, third one is less than 2000, the fourth one is 2000, and everyone else after that is also 2000. The thing to note here is that if this p-par, ls, etc. had values less than 2000, they won't be included here because of using TakeWhile. If you want all of those students with less values, then we could use filter. That if the data is sorted, like in this case it is sorted, for example 1994, 95, 97, and then filter would be better, because we won't be then TakeWhile would be better, sorry, instead of filter, because in filter we'll still pass in all of these elements instead of whether their predicate value is true or false. But in TakeWhile it would stop here and won't execute on this value, I think. And drop while would just drop these and return everything else. Using map and filter together. Here, for example, if we want to get this sequence 10, 30, 50 from 1 to 3, 4, 5, which is, for example, odd numbers in this sequence multiplied by 10, we'd first have to filter out the odd numbers, for example 1, 3, and 5, and then we need to map those odd numbers to such that they are multiplied by 10. For example, here, to do that, we can do it like this. For example, first we're filtering the sequence 1, 2, 3, 4, 5 using this predicate odd, and then this filter would return a sequence, right? As we can see here, it's returning a sequence, and then we can use map on that sequence, where the function would just multiply the elements by 10. Here they're doing the same thing but in two different steps. First they're defining a function, let's say, or no, not function, but a intermediate variable which contains only the odd filtered sequences. For example, here filter odd 1, 2, 3, 4, 5 would return a sequence, and then we're assigning the value of that sequence to this filtered symbol, and then we're calling map with the same predicate function on that filtered sequence. So this is a little more readable, but it's a non-idiomatic style. It's not preferred to write Clojure in this way. And this is something called a threading macro. So this is the sequence that we want to work on, and first we're using filtering using this predicate function, and then we're mapping the result of that filter using this predicate function. A macro is a construct that transforms code before it is executed. We'll learn about macros later on. Okay, so we will use this threading macro, so we need to understand how it works. Threading macro rewrites your code so that the result of each form is inserted at the end of the next form. This way we can write the following. So the result of this form, it would be simply 1 2 3 4 5, and it would be inserted at the end of this form. Okay, so here, for example, if you see here the result, this would be inserted here, and then this would be inserted at the end, which would be the same as this thing, right? This is just a syntactic sugar or shorthand, so we can easily understand what's happening here. For example, we're working on this sequence, and then we're first applying this, and then we'll apply mapping, etc. So it's more readable and more understandable that way. Now we'll learn something about lazy sequences. So range function will return a sequence from here 1 to 10, where 1 is inclusive and 10 is exclusive, meaning 1 would be included in the string or in the sequence, while 10 won't be included, or 10 would be, yeah, it won't be included. It would only go up to 9. Can we, for example, specify, for example, 10 to 1 and -1? Yep. So we can specify how much, by how much we want to increment the range. For example, here range 1 10, and we want to increment by 2. It would start at 1, and then it would, instead of returning 2 or going to 2, it would increment it, or it would return us the next or the next to the next element, which would be 3, and then plus 2, which would be 5. And here we're saying that we want to start at 10, we want to go till 1, and we want to -1 means that return sequence in reverse. So we would get 10 9 8 7 6 5 4 3 2. Oh, range 5. By default, if we only, wait a minute, can we look at source code? Yep. So if no argument is provided, it would, oh yeah, what would it do? It would just, oh, this is some Control C. That was cryptic. Source and range. If no argument is provided, it would when step is equal to 0, it returns an infinite sequence of start. So it's just incrementing 1585.704, 1585.705. It is just incrementing from 0 till infinity, I guess. I mean, it just keeps on running. And if only a single argument is provided, it is treated as an end argument, or where the range should end. Here start and end, start, end step. Okay. Okay, so range is a lazy sequence, and it's, yeah, I mean, it's evaluated lazily, for example. And one thing to remember is that if we are using the range function in the REPL, we can see that it's evaluated instantly, but this behavior is only in the REPL, not in, for example, other running environments. But to see if it is evaluated lazily, really, we can assign it to some variable, and then, for example, let me just our sequence is being evaluated. Currently, in lazy evaluation, once we need something, an element or a value, it's evaluated then, and it won't be evaluated beforehand, unlike in other sequences. Okay, map, filter, and remove are also lazy. Okay, to see how laziness affects our program or how it's evaluated, we're going to define a new function called range, which would have some side effects, so we can see how laziness works or affects our program. So we're defining a function range which takes a single argument called limit, and it would just use the TakeWhile function with the predicate where we're seeing if our element is less than the limit, and then we'll iterate 0. This is, I guess, an infinite generator. Okay, so here this would return, for example, here we can see this, it would keep on running and incrementing, but TakeWhile would stop using this function or evaluating the next element when this predicate value returned is false. So if we reach the element that's bigger than or equal to the limit, then it would stop executing. So if we call our range on 5 where the limit is 5, so it would start at 0 and then increment until it reaches 5. And then we can use map to multiply each and every element in the sequence with 10, and we're calling it on our range 5. So as expected, yeah, it's working as expected. Multiply. So now we'll use a side effect function map, which takes an anonymous function, and the anonymous function takes I as the first argument, and then just prints a dot, and same as before, our range 5. And why 2 dots there? So this dot is of this 40. Yeah, here this dot was before. Okay. The exact position of the dots may be different when you try this. They may appear before or after the list of integers. They are not part of the result sequence. They are being printed simultaneously just before each multiplication is executed. There is a 1 dot for each integer because the entire sequence has been realized. They are just being printed, but I thought that this is a complete or a sequence is returned like this, but I guess this is just printing each and every element in the sequence. So the first dot, it's starting a sequence, the first dot will be printed, and then another dot will be printed for the next element, and then the first element value, and so on. Okay, so we'll use def by 10 to create a symbol that would bind the values or the map function to this by 10 symbol. And so this would create by 10 symbol, but no dots have been printed yet because nothing has been executed yet. And if we call by 10, it would then evaluate everything. So that's lazy evaluation. The computation is all the values are evaluated when they're called. Here we're using that macro. What was the name of that macro? Expanding macro, or what was the name of macro? Threading macro. Yeah, it was called threading macro. So we're using the threading macro where the sequence that we want is range which would return us a sequence from 0 till the largest number our system can handle. And then we're calling map on that sequence, so we're multiplying each and every element by 10, and then we're just taking the first 5. So not all of the sequence would be evaluated, only the first 5 elements of the sequence would be evaluated. So this is the benefit of lazy evaluation. So if we need to create some sequence of random numbers in JavaScript, we would do something like, for example, var ints is equal to this empty array, and then, for example, we'll use a for loop where it would run for 20 turns, 20 times, and then we would simply push a math.round. So with math.random number times 100, which would make it from 0 to 100, and then we would use round, and then we would push that into the ints. So there is a rand int function in Clojure which returns a random integer, and then there's a repeatedly function which returns a lazy sequence of calls to whatever function we pass it. So for example, here if we call repeatedly on partial, randint, and 100, it would randint 100. Wait a minute, let me just see what rand 100 would do. So it would return a random integer in the range of 0 to 100. Okay, and what partial did? The partial takes a function f and fewer than the normal arguments to f and returns a function that takes a variable number of additional arguments. Okay, why use partial here, and why we aren't using just randint instead of? For example, if we call repeatedly partial round 100, it would repeatedly call this. How to stop? Do we have to Control C always? First, let's just use this take 10, and we can call repeatedly the randint function, and take 10 from the repeatedly randint 100. It is partial. Oh yeah. Randint 100 here. Random integer 100 would return a integer, a value, for example a number. So but repeatedly expects repeatedly a noun that calls randint with a fixed function. Repeatedly expects a function. For example, we can use repeated function which returns a lazy sequence of calls to whatever function we pass it. So to create instead of randint evaluating randint, we can use partial. So here partial would return this random integer function with this argument. So this would return a function, and then repeatedly would create or return some lazy sequence of calls, and we can only take or lazily evaluate the first 10 calls. So this would return first 10 random integers. And yeah, we can just write a little anonymous function instead of partial. And to create a function, for example some random integers which takes a size argument called size, and then we can take the number of arguments provided by the size from the repeatedly anonymous function. Here they're using anonymous function. We can use partial or this shorthand notation for anonymous function or this longer notation for anonymous function, and it would all result in the same thing. Activities. The activities and parsing CSV in 12. Okay. Common idioms and patterns. We knew about this paradigm or this syntax already, not paradigm, this shorthand syntax. There they're saying that we can use anonymous function. Instead of doing that, we can quickly do this, and here we'll have to provide some argument names, etc. And here we can use this percentage sign 2 and 3 and 4 to specify to the second and third and fourth argument. And yeah, if we have more than 2 arguments, then using this, for example, this syntax, it would be ambiguous, or we won't understand what 4 meant or what 3 meant. Instead, if we used descriptive names for the arguments, then later on it would be better to debug or understand that code. So if we have more than 2 arguments, then it's better to use this notation, and if we have fewer than 2 or 2 arguments, at most 2 arguments, then this notation would be better, as it is more succinct and yeah, and more easily understandable and readable. Yep. So with function literals we cannot nest multiple functions inside. For example, here if I want to create a function literal, let's see this function literal which calls map, and another function literal, let's say this is less than 10, and here this. So now this is just for example. The problem here is that this percentage sign, we don't know which function literal it's associated with. Is it this one or is it this outer one? So because of that we cannot use nesting inside a function literal. And whenever, for example, something or some function becomes complex, it's better to switch to fn form instead of the function literal form, because it's more readable and less error prone. Yep. So here, for example, to this would the partial function returns this first argument preloaded, where the first argument to this function would be 10, and then it would pass this to that and return, and pass this to that and as the second argument to this function and return the value, etc. Here the partial function returns a new anonymous function that is multiplier with its first argument preloaded. For example, here if we define a part to be this partial function and then call a part with 5, it would multiply this 5 by 10. And we can use the keyword as a function as we've already seen. So if we use this keyword and provide it a map, it would return the value associated with this key in the map. So it would return 42. Let's just do this. We'll define a map called player, and okay, yeah, let's just work it out here. use map to return a vector of current points for each user. So we can write, for example, map. This is the function, predicate function, which takes a single argument player and returns the current points of that player in the game users. So it would just look at this current points 45, and we can also rewrite this expression using keyword. For example, here we would just simply provide this keyword function current points, its keyword, as a function to the map, and it would return the same thing. So it would be treated as a function, just like it's being done here. Now let's just quickly define this game user variable. Okay, now the statuses that we want to keep, we'll define a set. For example, we want to keep the active, imprisoned, and speed boost. Okay. Here we just want pending or terminated status. We only want scores for players who have the pending or terminated status. So aside from these, we are keeping only this. Keep statuses. Write a function to extract the status field from each map and call the predicate on it. There are several ways you could do, maybe the first. So we can do something like, for example, filter. This is a predicate function on the game users. So we can filter such that so here the game user would for example, this element or this player gets passed to this function, anonymous function, and then we can, for example, call keep statuses on this function active. Where was keep status? Here. Keep status is as a set, and if we call keep statuses on something like active, it will return active, right? So here what we're doing is, and if that status is not present, it will return nil, which is a falsy value. Remember that. So what we're doing here is that first we're getting the status of the player. For example, here in this case the status of the player is active, and then we checking to see or getting, for example, using this syntax, we're seeing if keep statuses has active in it. If it has, it would return active, which is a truthy value. If it doesn't, it would return nil, which is a falsy value. So because of this, returning true or false, we can filter out all of those players that have the active status or whose status is in this keep status, that have active or imprisoned or speed boost. And we can use comp function, which is probably short for compound. Composition, yeah, it's short for composition. It is a composition of functions. For example, here comp function creates a new function which is a composition of two functions, keep statuses and this status keyword function. So comp function, which takes two functions and returns a new function, which is the result of calling the first function on the result of the second function. So this would call this keep statuses on the result of this. So first it would call this, it would get evaluated to some value, some result, and then it would call this function on the result of this function. And then we can use a threading macro to do this function or this functionality, like so. For example, we want to use game users sequence. For example, this is a sequence that we want to use, and then we can perform filtering using the comp function, where instead of defining keep statuses here, we're defining it inline. This is a set, okay, and then where this is the first keyword or function, and then this is the second, or this is the set, and this would call this. For example, here where keep status is, instead of using this symbol here, we're directly using the set here. So for example, active, and let's just say passive, and we can call it like so. And yeah, so it's doing the same thing as this and this in a single statement. For example, it would filter, it would composite or create a composite function of this set, which will act like a function, and this status. For example, here status would return active. Let's say it would return active, then it would check to see if active is present in this set or not, and then it would map current points. So it would only return the current points of the filtered students. So if we run that, here we can see only the users that have a status of active or imprisoned or other speed boost would be returned from this filter, and then using map we are only interested in the current parts. So map here, this is the first map is the function name, this is the predicate function, that is the first argument of map, and the result of performing this filter, which would be a sequence, would be added at the end there because of this macro, threaded macro. So the limitation with map is that it would always return the same, for example, the output sequence would have the same length as that of the input sequence. But if we want to append or increase the length of the output sequence, we can use something like mapcat. For example, in this case, there's an alpha lowercase symbol which contains some alphabets in lowercase, and we want to return a new sequence which contains the lowercase letter followed by its uppercase representation and so on. So using map, this won't be quite straightforward or possible, because the return or the length of the input and output sequence should be the same. But using mapcat, we can do this like so. Yeah, let's see how it's done. It's mapcat. It takes a function and a sequence. The function, it's taking an element and then it's returning a vector where that element plus its uppercase counterpart. Here the function we provided returns a 2-item vectors, and it would, so for example, this 2-item vector would be converted into a single sequence at the end. Mapcat simply unwraps each of these vectors so that in the end you have a single flat list. So mapcat would simply unwrap all of these vectors. It's useful for flattening a list. Okay, we can provide multiple sequences to the map function as well, but the caveat is that the function or the predicate function that is provided to the map should then have the same number of arguments as that of the sequences. For example, here we're providing 2 sequences, so the map function should have 2 arguments. And here we can, for example, add these 2 arguments or these 2 elements of different sequences. For example, by providing these 2 sequences of the same length and this predicate function, we can add all of these together. For example, 5 plus 5, 8 plus 2, 3 plus 7, etc. Okay, so zip map. Clojure already has a zip map function that takes 2 sequences and combines them together in a map. Let's try it out then. Zip map A, B, C and 1, 2, 3. So it would create a map where this one, the first one would be the key and the second one would be the value. Okay, and here we're defining our own zip map function. Define our zip map, which takes two arguments, xs and ys, and it's using a threaded macro where the first argument uh, would be a map function that maps, that simply returns a tuple or a vector containing two elements, and we're transforming it into a map. Unlike, for example, in Python, there's a specific type called tuple or named tuple, etc. But in Clojure, there's no special type, or yeah, there's no special type for a tuple or Clojure data structure called tuple. They simply refer to something as a tuple. If, for example, here this string, this vector, they simply refer to it as tuple because here the um, position of the argument represents something. For example, we can say, for example, we can map 5 and to x and 9 to y, but instead if we return tuple and assume that the first one would be x and the second one would be y, then they would consider it tuple. It's just for our understanding. A Clojure language doesn't have any idea of what a tuple is. So there's another function called map indexed, which for example, here let's just first define this function and what's being done here, and then we'll be able to explain this one as well. If we have, for example, a meals data set, a vector, and we want to display something. For example, we want to display the number 1 or 2 or 3, 4, etc. before the meal, then we can write a map function. For example, map, which takes two sequences, range and meals, and so the function should also take two sequences or two arguments. I'd say function index meal, and then we're simply concatenating a string where the first we're incrementing the index, because index starts at 0, we're incrementing it by 1. So the first one would be 1, the second one would be 2, etc. Then a dot would be appended, and then the meal. So this is the whole function. So this sequence is so common that in Clojure, this functionality is so common that in Clojure there's a specific keyword function called map index, which instead of using this range function, we can simply call meals, and range would be called for ourselves, or because of this it would be called, or I don't know if it would be called, or there's some other functionality, but it behaves the same way. So the function, it would still take index and meal. So, and we can, for example, again the index would start at 0. We first need to increment it by 1 and then meal. So in languages like JavaScript, Python, or C++, etc., we can use for example, to offset or access some value later on. For example, here we can access um, I plus 1 and I as well in the same function. Here we want to access our values I and our values I plus 1, which would, for example, in the case of 1 and 2 and 3, we can access this value as well as this, or this value as well as this, in a single loop. And it's pretty common and used a lot. But to access or achieve the same functionality in Clojure, we can do something like, for example, map, and this function that takes some two arguments, because two sequences will be provided, first and the next value. So first sequence would be my sequence, and the second sequence would be rest of my sequence, so it won't include the first one. For example, 0 1 2 3 4 5, the rest 1 2 0 1 2 3 4 5 won't include the 0, it would only include 1 2 3 4 5. So that way we can get this 1 as well as in the same function or code block. And if the length of the sequences provided to the map aren't equal, then map stops iterating over them when it reaches the end of the shortest sequence. So for example, if a sequence map has, let's just quickly, how about we just provide plus function. It takes variable number of arguments, so we don't have to define anything else, I think. And just let's provide 1 2 3 4 and 1 2 3 4 5 6 7 8 9. So we're providing two sequences, so the return value would be, or the return sequence would have the same length as that of the shortest sequence. So it would, for example, 1 plus 1 2, 2 plus 2 4 6 8, and 4 plus 4 is 8. And then because 5 has no other corresponding value in this other list, so it would stop executing and only return till this shortest sequence. I thought it would be bigger data structure. Anyways, so this is the temperature by day, and we want to write an expression that maps over this vector starting at the second item 23 and outputs either warmer, colder, or unchanged. Okay, so depending on it needs to have today as well as yesterday. So 2 days we need to look at two values at the same time. So as we learned in the previous section, we can use, for example, map. Should we use anonymous? Let's just go with map function today, yesterday, and it should, what did con do? What did con do? First I will have to quickly see what cont did. Cont takes a set of text expression pairs. It evaluates each test one at a time. If a test returns logical true, cont evaluates and returns the value of the corresponding expression. Doesn't evaluate any of the other tests or expression. So it would evaluate if any of them. It's kind of like and, I guess. If any of this is true, it would return the value and carry on. And if none of these are true, it will return nil. So we want to see if any of this is true, and hope probably one of this will always be true because we're checking for greater and less than or equal. So yeah, let's just go through it over here. We're creating a function that takes two arguments today and yesterday. Then we're defining cont, which checks to see if any of this is true and returns the value of that true statement. For example, if this is true, this condition is true, then it will return this. If this condition is true, then it will return this, and if this condition is true, then it will return that. So it takes a set of test expression pairs. This is the test and this is the expression. And it would evaluate the first expression that returns true. It would only return that and won't go any further. For example, if this is true, then it won't go any further or evaluate these as well. So this is the function body, and then we're providing two sequences to it. The first one, rest temperature by day. This would be today, as we're not taking into the account this first 18 yet. It would be 23, 24, 30, etc. So first time today would contain 23, and temperature by day, the first value would be 18. So here its first value would be 23 and its first value would be 18. And when we pass this as 23 is greater than 18, so it would return warmer. And if we take a look at, if we count this, then the size of this would be one less than the size of this because this this is the shorter sequence. For example, if the length of this sequence was 5, then rest temperature by day would be 4, so the output sequence would be the shorter one, and it would have the length of 4. I think it's enough for now, and I want to solve some foreclosure problems, and then we'll call it a day. Nowadays, I'm trying to learn more and more about quantum computing, and I'm quite interested in quantum machine learning and quantum reinforcement learning, and I'll have to do a lot of reading and learning as I'm not very good. I have some idea of linear algebra, but I'll have to study a lot about linear algebra and vector spaces and Hilbert spaces, and then quantum mechanics and Dirac notation and how qubits etc. It's a long and tough journey ahead, but we'll figure something out. So I guess, yeah, let's go with local bindings, nth element, let it be count sequence, regular expression, sum it all out. Okay, local binding. Clojure lets you give local names to values using the special let form. Okay, so let x5 the value of x is 5, and then if we add 2 to it, then 5 plus 2 is 7. Here the value of x is 3 and y is 10, so 10 minus 3 is 7, so it should be 7. And here the value of x is 21, and then another let block inside that, value of y is 3, and 21 divided by 3 is 7. Okay, nth element. Write a function which returns the nth element from a sequence. Special restrictions: don't use nth. Okay, I have completed this one before. Anyways, so here what we're doing is, okay, this is an anonymous function which has 2 arguments. The first one is the list, and the second one is the item or the nth item that we want to get. So first we're incrementing that by 1 because we want to include that. For example, 6, if we take 6, it would take the first 6 elements excluding the 6th element. If I guess, for example, 1 2 3 4 5 6 7. Okay, this is the list, and if we want to take 6, it would return only these first 2 6 values, but the index at the position 6 or the value at the index 6 is 7, and we should return 7, so because of that we increment it by 1 and it would be 7. So this is 7 now, and then we take the last element of that, which is 7. This is the sequence. Okay, so this should work. How about reversing or taking the first element where we drop 6. How about just using drop 6 1 1 2 3 4 5 6 7. It would only return 7, but if there were multiple other values it will return that, and then we can call first on that. So I guess that would run as well. So let me just, what was the, how to comment? Dog comment. Okay, Clojure comment. What was the symbol? I guess it was a semicolon. Not comment block, I want. Double semicolon. Okay, so if we comment that out, single also works. Okay, so we can define a function called first which drops this second argument, and then we call drops second on first, and then we call first on that. How about that? Yep, it also works. Now let's look at some of the solutions. Teams, yep, this is what I did, and this is the same, and here, oh yeah, this is also very good. So he converted it into a vector. He converted that sequence into a vector, and then using the get syntax of the vector he simply got that. This is the same as this one. Okay, I like this one. Okay, let it be. Can you bind x, y, and z so that these are all true? Okay, x and y, it should be 10, 5, 5. Okay, and 5 minus 1. Okay, so z is 1. We know that. Okay, if let z is equal to 1. So x should be then 7, y is 3, and c is 1. Right? 7 plus 3 10, 3 plus 1 4, and 1. Yep, it works. No need to look at that. And then write a function which returns the total number of elements in a sequence. Special restrictions, count. Okay, we can't use count, and we have to return the total number of elements in a sequence. Okay, so that's going to be tough. So how to I was thinking about using sum in a way, but so we need to count the total number of elements in a sequence without using count. And sequence could be anything. It could be a list or a string or a vector inside a vector or a single. Is this a single list, right? Yeah. And keywords etc. Okay. How about we can use first and rest, I guess. While rest etc, we can sum it. Sum value. Recursive function, yeah. We can use a recursive function which sums tells some value. But that would be too complex. I guess there should be a simple way. If we define my count which takes a list and here it takes a list, define my count, then okay, we'll learn something regarding this. Or should we use if else? If rest, if not rest, then Well, let me just quickly try this. If rest then I want to call my count on rest plus 1. The else if then it should just return 1, and then we can, I don't know what I really did here. 4 execution error, wrong number of arguments passed to user my count. Really? I am providing a list. And wrong number of arguments passed to user my count. How about we use this as it? Okay. Did you learn about passing list as an argument or a sequence as an argument? Okay. What is the next one? Regular expression, later, sum it all up. Numbers. Oh, another thing we can do is, for example, we can do map and what was the function that returned always true? Function that returned always true. Never mind. It was getting started with filter. I guess in filter odd remove constantly true. So we can use constantly 1 and 1 2 3 4 5. That would return big, and we can do hello. Yep, I guess we figured it out, but I also think that it's not a very good solution though. For example, we can call plus on this map where we're constantly replacing or mapping everything to 1. Basically we're just counting it, and then okay, first how to call plus on a sequence. We can, what does reduce do? I guess we can use reduce, but first we'll have to look at its documentation. Yep, I guess we can use reduce plus and the 1 2 3 4 5. Yep, so we can use reduce plus that, and the length is 1 2 3 4 5. So it's working, but I'm not sure if it is a good solution. It is a solution, but not a very good one, I think. So we can use the first argument. Yes, and let's try to run it. Unmatched delimiter. We're closing this or run. It's working perfectly, but let's look at some amazing solutions which we never mind. So this is defining a function which takes a single argument s, and then he's again calling f on s using 0. If it's a single argument, it will return 0. If it's multiple arguments, it will return if empties or recurrent. Here I wasn't able to code. This is loop. We haven't learned about loop, so let's forget about that. This is reduce function. It takes c inc c 0. I have no idea what is happening here. And here partial apply plus partial. I guess we'll learn about apply here. We haven't learned what apply does yet.